The Standard Deviants present the deep-fried world of organic chemistry.
Remember that we told you carbon, in its ground state, only has 2 unpaired electrons for bonding? We've explained how hybridization makes it possible for carbon to bond to 4 hydrogens instead of only 2. But why does it need to go through the whole hybridization process? Boredom? A rebellious streak? Pure malice? No, listen up.
Earlier, we told you that all the orbitals in the same subshell are at equal energy levels. This means that all the electrons in all of the orbitals in the 2p subshell will have the same energy. But what about the electron in the 2s orbital? The s orbital isn't at as high an energy level as the 3 2p orbitals. Let's think about the central carbon in methane again. If we tried to distribute carbon's 4 valence electrons into 1 2s orbital and 3 2p orbitals, we would have a totally irregular, funky-looking methane with different types of carbon-hydrogen bonds.
We told you a little while ago that electrons like to be as far apart from one another as possible because they repel each other. This is where orbitals come in handy.
When orbitals are all at the same energy level, the electrons in the orbitals are able to maximize the distance between themselves, and the bond angles from that atom are all equal. If the orbitals holding the bonding electrons in the carbon of methane were at different energy levels, the bonds to hydrogen would be too close together, the bond angles would be all skewed, and the molecule wouldn't work because carbon would have to spend all its time suppressing mutiny because its electrons couldn't get along.
Arr! This is a mutiny!
So to avoid mutiny, the central atom simply resorts to the much easier method of hybridization. By combining the 1 2s orbital and the 3 2p orbitals to form 4 energetically equivalent sp3 orbitals, the central atom is able to bond 4 substituents at equal bond angles and avoid being overthrown. That is why carbon is so cool. It's the great mediator.
Other atoms adopt this same sp3 hybridization state to form molecules. They include the nitrogen atom in ammonia, NH3, and oxygen in water, H2O. Nitrogen with 5 valence electrons has 3 hydrogens and a pair of unshared electrons, which occupy the 4 hybrid orbitals and give ammonia its pyramidal shape. In water, the 2 hydrogens and the 2 unshared electron pairs bonded to oxygen occupy the 4 sp3 orbitals and give water its unique wedge shape.
We should mention here that once hybridized, a central atom doesn't have to remain hybridized, with 4 sp3 hybrid orbitals bonded to 4 substituents. For example, if the central carbon of methane is ionized, meaning it loses an electron and so has a net positive charge, its hybrid orbitals will rearrange themselves to accommodate the new electron configuration of the ion. If carbon were ionized to form a carbon cation, it would only have 3 valence electrons.
English! Please!
Sorry. Right. If the carbon lost one of its electrons so that the atom had a net positive charge, which also means that it is a positively charged ion called a cation, then that carbon atom would only have 3 valence electrons, right? If that happened, the carbon would only be able to bond to 3 bloody hydrogen atoms. This is what happens in the case of the methyl cation CH3+.
But we told you that in its ground state, carbon should only be able to bond to 2 hydrogens, and that in its hybridized state, it should bond to 4 hydrogens. Methyl cation has 3 hydrogens, which are at equal bond angles from one another. But if the central carbon is normally bonded to 4 substituents and is sp3 hybridized and has 4 orbitals, how is this possible? Let's start at the beginning and figure out what happens to carbon's electron configuration when it's ionized, which is what happens in the case of methyl cation.
Carbon's normal ground state valence electron configuration is 2s2, 2px1, 2py1, 2pz, for a total of 4 outer valence electrons. We just showed you how carbon is hybridized to form 4 sp3 orbitals, which hold 1 electron each. When the carbon in a carbon compound loses an electron and forms a cation, its normal valence electron configuration becomes 2s2, 2px1, 2py, 2pz, because it's been ionized and has lost 1 electron, giving it a positive charge.
We just told you that the methyl cation only has 3 hydrogens and that they are equally spaced around the central atom. What does this tell us about the state of the central carbon cation?
It votes Republican?
No!
It drinks decaf?
No!
It's a licensed investment banker with a 70-foot yacht and a house in the Pyrenees.
No! Gats!
It tells us that the central carbon has rehybridized itself to accommodate the 3 hydrogen atoms. Let's look at the carbon cation's valence electron configuration again.
One of the 2s electrons is promoted to the empty 2py orbital. There it goes. But there are only 3 electrons to go around, and the carbon only needs 3 energetically equivalent hybrid orbitals. So the 1,2s orbital is combined with 2 2p orbitals to form 3 hybrid sp2 orbitals. They are called sp2 because they're formed from 1s and 2p orbitals. The third p orbital, 2pz, remains empty and uninvolved in the hybridization process.
Each hybrid sp2 orbital contains 1 electron to bond to a hydrogen atom and form the methyl cation CH3+. The configuration of the hybrid orbitals looks like this: sp21, 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 pz. The new sp2 hybrid orbitals, constructed from the 2s, 2px, and 2py orbitals, will have sort of a distorted shape because they are made of a combination of 3 different orbitals. Each of the 3 sp2 orbitals looks like a distorted mushroom pointed toward the corners of an equilateral triangle. This gives the methyl cation its particular trigonal shape and its very specific carbon-hydrogen bond angles of 120 degrees.
What about the unused 2pz atomic orbital? It's empty and lying perpendicular to the cation's trigonal plane, ready to accept a pair of electrons from a willing donor, a Lewis base. Because it's in the position to accept a pair of electrons, it is a Lewis acid. Other atoms can also adopt the trigonal sp2 hybridization scheme. For example, boron trifluoride has a trigonal planar shape, but if we look at boron's hybridization scheme, we see that it's the same as carbon's hybridization scheme in the methyl cation we looked at a minute ago. The orbitals of boron in BF3 are just like the orbitals of carbon in CH3, the methyl cation. Let's look at another badly named species, triplet methyl carbene, CH2. This intermediate is not an ion, so carbon still has all 4 of its valence electrons, but only 2 electrons are required to bond the 2 hydrogens necessary to form this molecule. Chemists know that triplet methyl carbene has an almost linear arrangement between the 2 hydrogens. Therefore, hybrid orbitals must be involved so that the species' 2 carbon-hydrogen bonds will be equivalent. In the linear hybridization scheme, 1 electron is promoted from the s orbital to an empty p orbital. For the mixing process, only 1 s and 1 p orbital are used, creating 2 sp hybrids. The remaining 2 p orbitals are left alone, and triplet methyl carbene's hybridization scheme becomes sp1, sp1, py1, pz1.
The 2 new sp hybrid atomic orbitals have a distorted mushroom shape and point in opposite directions, yielding the linear arrangement and 180-degree bond angles. In fact, this arrangement is the result of mixing only 1 p orbital and 1 s orbital. The py and pz orbitals each contain 1 electron and lie perpendicular to the linear axis of the molecule. We'll eventually see how the sp hybrids and the unused p orbitals on carbon are used to form triple bonds. Beryllium chloride, BeCl2, is another molecule which utilizes sp hybrids to produce a linear arrangement.
Bet you never thought carbon could be so interesting. Scientists have set aside an entire subdiscipline in chemistry devoted solely to carbon because it's so keen.
As we go along, try not to feel overwhelmed. See, that's one of the great things about organic chemistry. It's a very logical science. And once you get the basics down, you'll have organic chemistry figured out. There aren't any surprises. Each new step builds on the previous step. So if you master the basics now, you'll master organic chemistry.
And what are the basics? Time and again, everything in organic chemistry boils down to what the electrons are doing. This is a very nosy science. One of the most basic principles in all of organic chemistry is that molecules with a lot of electrons like to interact with molecules without a lot of electrons. This principle will be the guiding star to lead us through this entire science. Part 4. Alkanes.
The simplest class of organic compounds is the alkanes. There are two defining features of alkanes. One, alkanes are made of only carbon and hydrogen atoms. For this reason, alkanes are considered to be part of a singular group of molecules called the hydrocarbons. Two, the only type of bond in an alkane is a single bond. In a single bond, only 2 electrons are shared between 2 atoms. And in case you thought all that hybridization stuff was a waste of your time, single bonds form between sp3 hybridized carbons.
So, what's that mean? Well, a single bond forms from the overlap of 2 sp3 hybrid orbitals. We just established that. 2 electrons are shared in this single bond, which we can also call a sigma bond. And that's it. Pretty simple, huh?
Okay, I see how organic chemists diagram these compounds, but how do they do something more basic? Name them.
I heard they name them after girls they really like, man. Kind of like the way they name ships. But the one doesn't hear the special warning that there's a big iceberg, and it goes right into the iceberg, and it starts to sink. Watertight safety compartments, they really aren't. And it's going glug, 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 glug. And all of a sudden, your mom's floating away in a lifeboat, and you are sinking down like this candle is sinking down in my heart, man. And it's dark, man, and you've just got a treasure chest next to you full of nothing.
Please note, this doesn't always hold true. There never was a pretty woman named Titanic.
Section A, naming alkanes.
Remember, there are a lot of different organic compounds that have a lot of different names. But certain compounds with similar structure and composition are grouped into classes, which all have the same types of names to help you keep them straight.
All alkanes have names that end in ane, and all alkanes are named on the basis of how many carbons they have. We've already talked about the simplest alkane, methane, which only has 1 carbon atom and 4 hydrogen atoms. The next simplest alkane is ethane, which only has 2 carbon atoms and 6 hydrogens. Propane is a chain of 3 carbons, and butane has 4 carbons. It's really important for you to learn the names of these first 4 alkanes, because you'll be using them all the time in organic chemistry. To help you remember them, here's a little song.
1 carbon in your alkane, and you're dealing with methane. 2 carbons in your alkane, and you've got ethane. 3 carbons are necessary for propane. And if you've got 4 carbons, you've got butane.
So the first 4 names are kind of a pain to remember. But, surprise! As the molecules get bigger and more complex, their names actually get easier to remember.
After butane, the prefixes begin to signify the number of carbons in the molecules. Pentane, for example, is an alkane with 5 carbon atoms, and hexane is an alkane with 6 carbons. Heptane, of course, has 7 carbons.
Okay, quiz. If a stop sign has 8 sides and is an octagon, and a group of 8 singers is an octet, what do you call an alkane molecule with 8 carbon atoms?
Signane. No. Gonane? Ethane.
Nope.
Octane.
Right. And 9 and 10 carbon molecules are nonane and decane, respectively.
Suppose you have an alkane that you know has 22 carbons. How many hydrogens does it have? Well, we can figure it out 2 ways. One, we could sit and draw up 22 carbons attached to each other and then start filling in all the remaining valence electrons with hydrogens. But that would take a long time, and we might make mistakes. Instead, we can figure out how many hydrogens there will be in a 22 carbon alkane using this general chemical formula, CnH2n plus 2, where n equals the number of carbons in the alkane. So if the mystery alkane we're dealing with has 22 carbons, We plug 22 in for N, and we see that a 22-carbon alkane will have 46 hydrogens. No sweat, right?
So far, all the alkane compounds we've looked at have been chains of carbons in a single line and are appropriately named straight-chain alkanes. But the cool thing about a group of carbons is that they don't have to line up in a long chain to bond to each other. Perhaps you're wondering if there's any other way to put these carbons together.
There is. Some alkanes are branched chain alkanes. For example, this butane molecule is a straight chain of 4 carbons, but we could also arrange the carbons so that 3 of the 4 carbons are in a chain and the 4th carbon is attached to the middle carbon of the bigger chain. But now this molecule isn't butane anymore, so how do we name this puppy? Easy, we just ask somebody else. Oh, all right, we'll tell you.
Just count the number of carbons in the longest chain. In this case, the longest chain has 3 carbons, so it must be some sort of propane. But there's more going on here than simple propane. There's a single carbon attached to the central carbon of this propane chain, and we just told you that methane is a 1-carbon alkane.
But methane's central carbon has 4 hydrogens, and in this drawing, the central carbon only has 3. Where's the 4th hydrogen?
I don't know, maybe hiding?
No, it's not hiding. The methane has lost a hydrogen so that its 4th valence electron can form a carbon-carbon bond with the middle carbon of the propane chain. When a hydrogen is removed from an alkane, as one was removed from methane in this example, we call the remaining portion of the alkane an alkyl group. Since the methane is no longer a true methane, we drop the ANE and add YL to signify that the parent methane has lost a hydrogen and is now the alkyl group methyl.
The methyl is attached to the 2nd carbon of the propane chain, so we're going to attach a great big old 2 to methyl, so we're certain of where that methyl is on the propane chain. Put it all together and we have 2-methyl-propane. Actually, if the methyl group on carbon 2 were attached to either of the carbons on the end of the propane chain, the name of the molecule would be 1-methyl-propane, but that's just regular old butane.
Just a quick note on alkyl groups. Like we said, when an alkane loses a hydrogen, we drop the ANE ending from the name of the substituent and add a YL. For instance, if ethane loses a hydrogen, we call it ethyl. Propane becomes propyl, butane becomes butyl, and schnauzer becomes schnauzl.
Now, there's something we need to point out here. We know the molecular formula for butane is C4H10. 2-methylpropane also has 4 carbons and 10 hydrogens, which is the same molecular formula as butane, but it's a completely different compound than butane. Butane and 2-methylpropane have the exact same numbers and kinds of atoms. We say that butane and 2-methylpropane are isomers of one another. Isomers have the same molecular formula, but different structures. You may remember from biology or chemistry that the prefix iso means same, and that's how it's applied here.
So they're the same, only different.
Exactly. And actually, that brings up a whole other topic. Let's take a look at 2-methylpropane again.
No.
Come on. It'll be painless. Don't be such a baby.
Here's 2-methylpropane again. Remember, we just told you that 2-methylpropane and butane are isomers of one another.
A long time ago, when organic chemists first began to play around with these compounds, all of these strict naming rules hadn't been invented yet, so they just sort of winged it. And, well, those names have been around for so long that when someone actually did try to come up with the strict naming rules, everyone just said, hey, why fix it if it ain't broke? So they just let some of those names stick. And that's how we got isobutane.
Isobutane is the common name for 2-methylpropane. It sort of makes sense, right? Because all they're saying is that isobutane is an isomer of butane. Of course, by today's standards, this molecule is called 2-methylpropane. But we can basically guarantee that you'll come into contact with the name isobutane, so you'd better know it.
Let's look at butane again. Like we said, when an alkane loses a hydrogen to bond to something bigger, we drop the ANE ending and change the name to alkyl. And here's where things get tricky. We've assumed that the hydrogen that's getting kicked off is one of the hydrogens on the end of the butane chain, and we've named the leftover alkyl group butyl accordingly. But what if a hydrogen gets knocked off of carbon 2? Is the name still butyl? Nope. And we kind of have to have a long discussion to figure out what we do call it. So find the remote, sit tight. Here's where the R's come in.
Do you see this carbon here with one R and 3 H's attached to it? Well, what that's telling us is this carbon is attached to one other alkyl group. Remember, an alkyl group is just an alkane that's lost a hydrogen in order to bond to this carbon. R is a shorthand for an alkyl group, just like the atomic symbol C is shorthand for carbon. So the R just tells us that there's an alkyl group there, and that tells us that there's a carbon there. That alkyl group could be methyl or ethyl or propyl or any other alkyl group. We don't know, and we don't care. All that's important is that we know that the R there is telling us that there's a connection to a carbon there.
And H just means hydrogen, of course. So, this carbon here with one R and 3 H's is attached to one other carbon and 3 hydrogens. We call this type of carbon a primary carbon because it's only attached to one other carbon.
And now, check out this carbon with 2 R's and 2 H's. That lets us know that our carbon is attached to 2 other carbons and 2 hydrogens. We call this type of carbon a secondary carbon. And this carbon here, with 3 R's and only 1 H, is called a tertiary carbon because it's attached to 3 other carbons. Finally, this carbon here, with 4 R's attached to it, is called a quaternary carbon. Got it? Primary, secondary, tertiary, and quaternary.
Primary, secondary, tertiary, quaternary. The shorthand for primary is a 1 with the degree superscript. The shorthand for secondary is a 2 with the degree superscript. The shorthand for tertiary is a 3 with the degree superscript. And you guessed it, the shorthand for quaternary is a 4 with a degree superscript.
And the shorthand for Jenny is a J with a degree superscript.
Let's look at butane again. This carbon over here, on the end of the butane chain, is attached to one other carbon, so we know that it's a primary carbon. And this primary carbon has 3 hydrogens attached to it. Those hydrogens are called primary hydrogens because they're attached to a primary carbon. Simple enough.
But carbon 2 in butane is attached to 2 other carbons, one over here on the end of the chain and one over here right next door. Since carbon 2 is attached to 2 other carbons, carbon 2 is a secondary carbon. And yep, you guessed it, the hydrogens attached to carbon 2 are secondary hydrogens. Make sense? Carbon 3 is also a secondary carbon because it's got 2 other carbons attached to it. And the hydrogens on carbon 3 are also secondary hydrogens. Carbon 4 over here on the end of the chain is a primary carbon again because it's only attached to one other carbon. And the hydrogens attached to it are primary hydrogens.
So, like we were saying, if an N hydrogen is knocked off of butane so that it can attach to something bigger, we change the name butane to butyl. Butane has lost a primary hydrogen in order to do this. But what if butane wanted to knock off a secondary hydrogen in order to bond to something bigger?
Let's say butane kicks out a hydrogen from carbon 2. Butane has kicked out a secondary hydrogen from a secondary carbon. So we can't call it butyl because, well, it's not butyl. It's sec-butyl.